This is the first mechanical neural network that my group built for the purpose of attempting to demonstrate the ability for a physical material to learn desired behaviors with repeated exposure to external loading conditions. The only problem was that after a year of failing to get it to work, we gave up and built a much improved mechanical neural network that did successfully learn to acquire the desired behaviors. Ironically, however, our failed machine was in many ways more instructive than our successful machine in helping us learn about what is important for enabling physical systems to learn. And so, I decided to make a video about our failed mechanical neural network to highlight what important insights we learned about mechanical neural network learning. To understand the concepts underlying this video, I recommend you first watch this seminal video, which introduces how mechanical neural networks learn in general. A link to the video is provided in the description below. After fabricating this mechanical neural network, we wanted to train it so that it would learn to achieve two shape morphing behaviors simultaneously. For the first behavior, we wanted the network's two output nodes to displace to target locations that lie along a sinusoidal curve when the network's two input nodes are loaded with equal horizontal forces, as shown here in red. For the second behavior, we wanted the network's two output nodes to displace in opposite directions to target locations that lie along an inverted sinusoidal curve when the network's two input nodes are loaded with equal vertical forces, as shown here in green. The mechanical neural network was built within a frame such that its two input nodes could be loaded in any desired in-plane direction using two pairs of voice coil actuators that independently drive each input node using decoupling flexures. The resulting displacements of the two output nodes were measured using two pairs of magnets and Hall effect sensors mounted within similar decoupling flexures. The axial stiffness of each of the mechanical neural network's 21 tunable beams, shown simplified here as blue lines, can be independently uploaded to each beam as desired. Each beam manifests these desired axial stiffness values by a closed-loop control using actuators, sensors, and flexures. A genetic algorithm was used to determine what combinations of axial stiffness values would be uploaded to the beams during the learning process, as the mean squared error calculated from the measured output node displacements was minimized according to the approach described in detail in our prior video on the topic. This plot is typical of the kind of plots generated by the mechanical neural network, showing the mean squared error progression from one generation of stiffness combinations to the next as it attempted to simultaneously learn the two behaviors mentioned previously. Note that instead of settling to a minimum and stable value, which would indicate that the network successfully learned the behaviors desired, the plot experienced disruptive jumps that never allowed the mechanism to achieve what it was attempting to learn. To understand why the mechanical neural network failed, it's important to understand its design and how it was made. The design's tunable beam was assembled by bolts using two layers of Teflon sheets, which were separated by aluminum standoffs. Flexure bearings, which guide the axial displacement of the beam, were cut within these sheets. Two stacks of small cylindrical magnets were embedded in the upper sheet and were used so two Hall effect sensors could measure the beam's axial displacements. A linear voice coil actuator was used to drive the beam's axial displacements and was mounted to a laser-cut wooden support, which was fixtured by 3D printed parts between the two Teflon sheets. Both the beam's symmetric flexure layout and choice of Hall effect sensors introduced significantly more nonlinearity than the latter beam design, which made it more difficult to control its axial stiffness. Note from this force displacement plot that the design was not able to fully achieve a purely linear response as it attempted to exhibit an unchanging axial stiffness value via closed-loop control while being loaded by an instron testing machine. Moreover, the Hall effect sensors produce significantly more signal noise than the strain gauge sensors of the improved mechanical neural network. And, despite there being two Hall effect sensors per beam, they experienced unwanted crosstalk from the magnetic fields induced by the voice coil actuators instead of exclusively experiencing the intended changing magnetic fields of their cylindrical magnet stacks as they move relative to the sensors. The entire mechanical neural network was assembled using similar parts to the single beam tested in the Instron, but it required only 2 large laser-cut sheets of Teflon to produce all 21 of its beams combined, along with the input and output node decoupling flexures. As a result, the design was not modular, and thus it was not possible to individually calibrate each tunable beam within the lattice, which proved to be very helpful to the success of the improved design. The mechanical neural network was mounted on a wooden box and was controlled from below by custom-designed control circuitry from within the box. When the network failed to learn, we tried building a different wooden frame around it so that nylon thread could be used to prevent the network's structure from sagging under its own weight. Despite that mitigation attempt, the lattice still produced plots with jumps in mean-squared error that never seemed to settle to a value small enough for the network to successfully learn its desired shape morphing behaviors. We suspect that the primary reason for this failure was because the system's loading response would occasionally change with unacceptably poor repeatability, so that the optimization algorithm's decisions were misinformed by outdated response data. There are multiple reasons for the poor repeatability, i.e. precision, exhibited by the mechanical neural network. First, due to the fact that the network was made predominantly from Teflon, it experienced stress relaxation and creep as a consequence of the changing voice coil actuator loads and gravity. Moreover, each beam's Teflon flexures exhibited hysteresis as they deformed due to internal friction caused by polymer chains slipping past each other as the flexures deformed. The clearance gaps between the voice coil actuators as magnets and coils were also not sufficiently large, and thus the magnets and coils would occasionally collide and rub past each other during learning, especially when the network sagged prior to using the nylon thread. This rubbing would generate friction and noise that would also contribute to the network's poor repeatability. Some of the network's many bolts and fasteners likely also loosened over time due to the vibrations induced by the step forces imparted by the input actuators during learning, which would also produce additional hysteresis. Furthermore, the symmetric flexures and rotational hinges at the nodes of the beams, in conjunction with the decoupling flexures of the input node actuators and output node sensors, produced a 2-layer flexure system which is highly overconstrained. Such overconstrained systems can exhibit nonlinearity and stress buildup, which also negatively impacts precision, i.e. repeatability. Finally, it's also possible that in instances when low-stiffness combinations were uploaded to the network's beams during the learning process, the flexures at the network's nodes occasionally yielded as they were driven unusually far, thus leading to significant hysteresis, since this version of the network was not designed with rotational hard stops at its hinges. In addition to including hard stops to prevent all of its flexures from yielding, the improved mechanical neural network was designed to overcome the other failings of the Teflon design so that learning could be successfully demonstrated. Since its flexures were made of aluminum, the improved design did not experience appreciable stress relaxation, creep, sagging, or hysteresis. This plot shows the first and fourth cycle axial force displacement response of its tunable beam. Note that hysteresis is barely apparent even when the plot is shown zoomed in over a much smaller range of deformation. The gaps between the voice coil actuators as magnets and coils in the improved mechanical neural network were selected to provide sufficient clearance so no bodies would collide or rub within the range set by the tunable beam's hard stops. Wedges were used to join each modular beam together via press-fit principles to prevent slipping while allowing the beams to be removed and reattached on demand for calibration purposes. The flexure bearings and strain gauge sensors within the improved network were also chosen since they are significantly more linear than the flexure bearings and Hall effect sensors of our initial design. This improved linearity made controlling the axial stiffness of the beams within the improved neural network significantly easier. The output node decoupling flexures of the improved network were removed entirely, and the input node decoupling flexures were adapted to include rotational blade flexures so that their input nodes would not be constrained to prevent rotation. Although still technically overconstrained, the flexures within the improved design constrain the system with significantly less overconstraint than the flexures within the previous design. Moreover, note that the electronics used to control the improved network were upgraded to being current controlled. This upgrade allowed the improved network to achieve greater force stability when learning dynamic behaviors while increasing the range of axial stiffness over which its constituent beams could be controlled. All of these improvements helped the new mechanical neural network succeed in learning where the previous design failed. Now, before I wrap up, I wanted to take a minute to respond to the most commonly asked question that I received from the comments section of the previous video about mechanical neural networks. Many of you wondered why the learning process is not just first simulated by a computer, so that a working combination of tunable stiffness values can be identified via computation and then uploaded to the mechanical neural network instead of the network itself having to iterate through different stiffness combinations that are actually tested live on the machine. It's a good question for which I have two, hopefully satisfactory answers. Firstly, it's important to recognize that there are some applications for which prior simulation is not an option. Imagine, for instance, a rover made of a mechanical neural network metamaterial that is sent to a distant planet to explore. It would be difficult to anticipate all the behaviors that the rover's material would need to exhibit for the mission prior to launch, and it would be time-consuming and sometimes impossible to send and upload a simulated solution from Earth such that the rover's network would achieve whatever new behaviors were found to be needed on the planet. Thus, having the rover's material physically learn autonomously in real time as proposed, without prior simulation, is essential for such an application. Secondly, and hopefully most convincing, it is difficult to take enough factors into account when simulating a system as complex as a mechanical neural network, such that the simulation produces accurate results. Relevant factors that may be considered when simulating mechanical neural networks include considerations of material and geometric nonlinearities that result from large deformations, dynamic inertial effects, fabrication and assembly imperfections and defects in the constituent parts, viscous loads from the ambient gas or fluid surrounding the network, thermal expansion loads from changing temperatures, and other relevant loads such as gravity, friction, or electromagnetically induced forces. Simulations that attempt to take even some of these factors into account typically require impractical amounts of time to run, and they typically end up crashing and ultimately fail to produce the desired results. Furthermore, attempting to simulate large mechanical neural network lattices consisting of thousands to millions of tunable beams while considering even a few of these factors quickly becomes computationally impossible, at least with current technology. Note that the simulated results that I presented in the previous video about mechanical neural networks assumed linear beam equations with quasi-static loading on relatively small lattices, and even those plots took one of the world's most powerful supercomputers almost a year to generate. You see, when mechanical neural networks physically learn as proposed, they take all of reality's factors into account, including ones that we may not even think to include in a simulation, and they do so in real time by definition, since they are operating according to the laws of physics, which act immediately and are never overwhelmed by considerations of computation. And with that, I'd like to thank and acknowledge my student Ryan Lee for making and testing the mechanical neural networks featured in this video. If you'd like to learn more, I encourage you to read our journal paper published in Science Robotics on the topic. Thanks for watching The Facts of Mechanical Design.